Alright, we're right back in it. Let's continue on.
And here, we run into one line. There's a pattern. Every time a pixel is inside the outline of B, we run into an odd number of lines going to the right. But if the pixel is outside the outline of B, we run into an even number of lines. The TrueType file format simplifies this concept even more by introducing a winding contour, which is a curve that goes clockwise, and a non-winding contour, which is a curve that goes counterclockwise. Whenever we test a pixel, we can simply add 1 every time we hit a winding contour, and subtract 1 every time we hit a non-winding contour. When we add it all up, we will get 0 if the pixel is outside the curve, and a non-zero value when the pixel is inside the curve. This brings up the question of how do we test if a pixel is going to hit a curve? In order to understand how we can check if a pixel is going to hit a curve, we first have to understand how a Bezier curve works. Let's start with the simplest Bezier curve, which happens to be a straight line. Imagine we have 2 points, P0 and P1. What if we want to represent the line between these 2 points using one function? When we input 0 to this function, we should get P0, and when we input 1 to this function, we should get P1. We will call this parameter t. If P0 is located at 10, 0 and P1 is at 20, 0, and I asked you what P of 0.5 is, what would you say? If you said 15, you guessed correctly. What about P of 0.75? Well, if you guessed 17.5, you guessed correctly. This makes a lot of sense to us intuitively, but what is our brain doing behind the scenes? We can abstract this into an equation pretty easily. We're simply doing 20 minus 10 times t plus 10. If we abstract this one more time, we can say more generally that P of t equals P1 minus P0 times t plus P0. Now we have one equation that can give us any line based off of 2 points. Let's rearrange this equation to look like P of t equals P1 times t minus P0 times t plus P0. We can factor out P0 and we get an equation that looks like this. P of t equals P1 times t plus 1 minus t times P0. Now that the equation looks like this, we can actually intuit what is happening behind the scenes. We're actually taking a weighted average between P0 and P1, which gives us our result. It will be helpful to think of a Bezier curve as a weighted average between all the control points. This is great, but this still doesn't help us figure out how to find a curve where a third point is the control point. Well, imagine that we now have a third point, and we want to draw a curve that bends towards that control point. When we define a Bezier curve, we want points P0 and P2 to have equal weight and how it bends towards P1. How can we do this? Well, let's draw 2 straight lines, one from P0 to P1 and the other from P1 to P2. We know that we can create an equation P of t for P0 to P1 and for P1 to P2. Let's call these lines Q0 and Q1. What if we just draw a third line from Q0 to Q1 and we create an equation to interpolate between them? Well, we can use the same equation as before. P of t equals P1 times t plus P0 times 1 minus t. We can rewrite this though in terms of Q0 and Q1. This would give us P of t equals Q1 times t plus Q0 times 1 minus t. And if we plug it all in, we get this. This will give us a nice Bezier curve from 0 to 1 that goes through P0 and P2 and is bent towards P1. We can graphically visualize this as an interpolation between Q0 and Q1 like this. Now that we can generate any equation for a Bezier curve using 3 points, we can find a way to see if a pixel is located at some position xy intersects with this line P of t going to the right. How do we check if a pixel will hit the curve? Well, let's imagine that the point xy is actually the origin. We can achieve this mathematically by simply translating each of our points, P0, P1, and P2, by subtracting the position xy. Now, if we look at P of t in relation to the origin, how can we tell if this point will intersect with P of t? Well, this is now just a simple question of finding the roots of this equation. We know that the equation is simply a quadratic function, and we should remember from pre-algebra that we can solve for the roots of the quadratic function using the quadratic equation. But our formula does not look like a quadratic function, so how can we find the roots? Well, let's rearrange our formula P of t. If we multiply all of the terms together, we get this. This still doesn't look like a quadratic function, so let's expand the multiplication next. Now P of t looks like this. Next, we'll distribute P0 and combine like terms. Ah, do you see it? There's now a quadratic function hiding in there. Let's factor out all the like terms and see what we get. Remember, a quadratic equation in standard form looks like y equals ax squared plus bx plus c. Looking at our equation P of t, we can clearly see what a, b.
Now, as far as this part, I'm definitely going to have to go over this. I need to get stronger with my math skills, apparently. But it seems like to me, I'm looking at this and I understand, but I'm trying to see, like, as far as like computers, how are we getting more power out of what we have? Like why, even though like you're doing the math to get more of the equations, right? Instead of one point to another point. But still, how are we getting more efficient by doing this kind of math to understand to get the to be able to bend and get the origin point? It's like you're taking a basic you're taking a basic number, right, and then breaking it down and breaking it down and breaking it down and breaking it down. It's like, how does that make things more efficient though? You know? How does that make things more efficient when you still, you know, it's 15 to 16, it's still 15 to 16, but it's like how do you get there? How are we getting there, and why does that make
B and C are? Now, to find the roots, it's a simple matter of setting the equation equal to 0 and plugging in the y coordinates of each point and solving using the quadratic equation. The quadratic equation will give us 1, 2, or no roots, depending on how many roots the function has. We can check each real root and see if the value t is less than 0 or greater than 1. If it's less than 0 or greater than 1, it will not intersect with our Bezier curve. If one or both of the roots is between 0 and 1, then we will intersect with the Bezier curve. Now we can test every pixel and see whether it will hit any of our curves simply by plugging in a few values. Using all of the combined techniques, we can now use a collection of points to define how a letter should be drawn. We can then connect these points using Bezier curves and determine whether a pixel should be on or off by testing it and seeing how many curves it hits. There are a myriad of other problems that you will encounter using this technique. Some problems to consider are, what happens when a pixel hits the junction between two curves? What happens when a pixel hits a horizontal line? What happens when a pixel is on a curve? The TrueType format sets out to solve all these issues with a complicated set of instructions that are defined to handle all of these edge cases, which I will not be covering. I hope that this video has showed you how something as simple as displaying text through a computer screen is not as simple as it may appear. If we take a deep dive into the mathematics behind it all though, we can see how you could create a procedure to transform a series of curves into the text that you look at on a daily basis. Thanks for watching.
So I didn't mean to get off track with my little rant back then, but this was definitely enlightening. So just to kind of go over it, this is a little deeper. The two type of file formats, BMP file, TTF file. I know what that is. Lagrange interpolation. Definitely want to look that up. math and curves. Bezier curve, I know what that is, but then he threw that other term in there called winding contour and quadratic equation solving. So I guess one of the reasons why I don't understand how the mathematic, like we all know what a fraction is and everything else, right? But that's my first time ever hearing about quadratic equations. So that's just a totally another way of doing math. And that's what these videos is for, finding out exactly what you could be lacking and what you can learn, because I never knew this even existed. I didn't take, let me see, we took algebra, but I wasn't that good at math in school myself. So that's something else I got to look into, is getting better at math to understand this. But again, the interesting thing is that I've been doing this for the longest time, and I didn't know this is exactly what I was doing. Just basically making pixels, moving around pixels and Bezier curves all day. That just blew my mind there. But yeah, so I think the main takeaway from this one is quadratic equations. Find out what those is, and that's a whole new level of math, a whole new level of doing numbers will open up. So yeah, the math behind font rasterization, GGW, GWG. Thank y'all for watching.